will talk about what is Weyl algebra, what is representation of algebra. We are going to talk about the representation of Weyl algebra in characteristic 0 for a bit. Then we'll move on to our main content, which is in characteristic p greater than 0. So first things first, what is Weyl algebra? So throughout today, our notation will be, we will denote by K to be an algebraically closed field. So why do we need this property of algebraic closure? Because in an algebraically closed field, we have roots of polynomials. And therefore, for linear operators, we have eigenvalues, which is not necessarily true for non-algebraically closed fields. So that's why we require this condition. So let's say K is an algebraically closed field, and we are gonna form this algebra, which we are calling the free algebra, with formal symbols K and X. Now let's slightly recap. What is an algebra? An algebra is a vector space along with a multiplication structure, such that the multiplication is compatible with the vector space structures, right? So Kxy is the free algebra over K with formal symbols X and Y. Then we are gonna quotient out Kxy by the ideal generated by the element Yx minus Xy minus 1. So this is the first Weyl algebra. So as you can guess, since I'm calling it the first Weyl algebra, there are many more Weyl algebras to follow, but we're gonna focus mainly on this first Weyl algebra today. So in this algebra, Yx minus Xy is equal to 1, because we have quotiented out the free algebra by this ideal, right? Okay. So we have defined Weyl algebra, and one can check easily that a basis for A1 is this: x to the power I, y to the power j, where I and j are non-negative integers. Why is this? Let me give you an intuitive idea why this should be the case. So suppose we have some formal symbol, let's say x, y, y, x, and so on. So here there are some x's after y. So we can move this x in the front using this identity that xy must be equal to yx minus 1. So using this, we can move all the x's to the front and all the y's to the back. So therefore, this will form a basis for this algebra. This will be the vector space basis for this algebra. Okay, so that's the intuitive idea of why this should be the basis. I'm not going to prove the linear independence or that this spans the Weyl algebra, but it should be clear to everyone, right? Any questions so far? So one question that one might have is that, why do we care about the Weyl algebra? What's interesting there? The thing is, the Weyl algebra pops up very naturally in quantum mechanics. Why? Because in Weyl algebra, Yx minus Xy is 1, right? Or in other words, the commutator of Y and X is 1. Does this look familiar? Of course it does, because in quantum mechanics, the commutator of the position operator and the momentum operator is I h cut, right? So therefore, Weyl algebra is basically the algebra generated by the position operator and the momentum operator. So yeah, so that's why we want to work with the Weyl algebra, because it pops up very naturally in quantum mechanics. Okay, and we can similarly define the nth Weyl algebra using n position and momentum operators, using the canonical commutation relationship of the position and momentum operators, right? So this is the canonical commutation relation. With a factor of I h cut missing, but we can work with that. But today we are going to mainly focus on A1, as we have already discussed. All right. So yeah, now we are going to talk about what is representation of an algebra. So a representation of an algebra is basically a way of expressing the algebra elements as linear operators. Okay, formally speaking, it's a representation of an algebra A is a vector space V along with a homomorphism rho from A to the endomorphism space of V. So in other words, given A is an element of the algebra, not necessarily. Well, the vector space can be infinite dimensional or finite dimensional, but the algebra is infinite dimensional as a vector space. But the representation space, which is V, the space on which the elements of A are going to act, that might be finite dimensional or infinite dimensional. Okay, so as I was saying, given any element of the algebra, rho of A is basically a linear operator on the vector space V. Okay, and this is the definition of representation of an associative algebra, or in other words, the multiplication structure on the algebra is associative, which is not really the case for Lie algebras. For Lie algebras, we have to define in such a way that this map rho from A to endomorphism space of V, this becomes a Lie algebra homomorphism. But we're not gonna go into that. We're gonna focus about this. So yeah, a representation is basically a way of expressing each algebra element as linear operators. Okay, and sometimes we're gonna write AV instead of rho AV, but we're gonna be very conscious about our notation, right? Okay, now the second thing, a subrepresentation is basically a subspace such that the image of that subspace under the action of A is contained in the subspace. So in such a case, we call U an invariant subspace under the action of A. Okay, and if there is no non-trivial subrepresentation, then we call the representation irreducible. So we're gonna focus on irreducible representations today because we can form other representations using the irreducible representations. So they are sort of the building blocks of the representation space. Okay, so far so good? All right. So yeah, now this is the definition of homomorphism of representations. Suppose we have an algebra A and we have two different representations of the algebra, meaning we have two vector spaces V1 and V2. On V1 and V2, the algebra A acts in some way. Then a linear map from V1 to V2 is called a homomorphism of representations if this diagram commutes for every A. Or in other words, if we use our abuse of notation as before, this looks like this. Phi of A V equals to A phi of V. Okay. All right. Is this clear? Okay. We are now covering some prerequisites to get into our actual content. Oh, right. And an isomorphism of representation is an invertible homomorphism. So it's a homomorphism of representations which is invertible. So this should be clear. Now we are gonna see a very pivotal result in representation theory, which is called Schur's lemma. That says basically, let's say phi is a non-zero homomorphism between representations. If the domain space is a irreducible representation, then the map must be injective. In the other case, if V2 is irreducible, then the map must be surjective. And if both are irreducible, then phi is an isomorphism. So the proof of Schur's lemma can be found in any standard representation theory textbook, but we are gonna quickly outline the proof. Is that we have to just look at the kernel of phi or the image of phi, and this kernel and images they form, so they are sub-representations. So as we are saying, if V1 or V2 is irreducible, then those sub-representations have to be either zero or the whole space. So in those cases, we get either kernel of phi is zero, in which case phi is injective, or image of phi is V2, in which case phi is surjective. All right, so this is the statement of Schur's lemma, and we are going to use it a lot. We have a corollary of the Schur's lemma that says that, let's say phi is a homomorphism of representations, where V is a finite dimensional irreducible representations. Irreducible. So we call irreducible representation in shorthand irrep. So let's say V is a finite dimensional irreducible representation. In that case, a homomorphism of representations from V to itself has to be equal to C, some constant C times the identity operator. So yeah, so this should be clear from this, because if both of them are irreducible, then wait. Yeah, so as I was saying, in this case, the domain space and the codomain space, both of them are irreducible representations. So which is why we must have that phi is some constant times the identity. And the proof is very simple. The proof is basically, since we're in an algebraically closed field, phi has some eigenvalue. Let's say the eigenvalue is lambda. Then phi minus lambda times identity. This is a homomorphism of, sorry, I made a mistake. This should be homomorphism of representations. So this is a homomorphism of representation from V to itself, and both the domain space and the codomain space are irreducible. And this is not an isomorphism. Why? Because it has non-zero elements in the kernel, right? So which is why it has to be zero, since it's not an isomorphism. And finally, we have another corollary, is that if an element is in the center, what is the center? The center basically consists of all the elements that commutes with all the other elements. So if A is in center, then rho of A must be a constant times identity. Why? Because if A is in the center, then rho of A is a homomorphism of representations, and which follows from the previous result. So that's about it for the prerequisites. Then let's see. So let's now talk about the representation of Weyl algebra in characteristic 0. So as I said, the Weyl algebra pops up very naturally in quantum mechanics, and which is basically the algebra generated by position and momentum operators. And in quantum mechanics, we deal with the nicest field, which is the field of complex numbers. It is algebraically closed. It has characteristic 0. And it has many more nice properties. It has a number which squares to -1 and so on. So there's a very important theorem in quantum mechanics, which is the Stone-von Neumann theorem, that says that every irreducible representation of position and momentum operators are unitarily equivalent to the usual ones, which is multiplication by x. This is the position operator, and the momentum operator is I h cut del x, del x. And in which representation space are these operators acting on? Well, in quantum mechanics, we work on L2 of R mainly, right? So on this space, these operators act on. And this is an infinite dimensional space. So we can say that every irreducible representation of Weyl algebra in characteristic 0 act on infinite dimensional space. Or in other words, the irreducible representations are infinite dimensional. All right. So yeah, the only irreducible representation looks like this. And well, and here I have picked a different vector space, which is the space of polynomials. I have picked this because this is the smallest space on which these operators act on, because this is countably infinite dimensional. However, L2 of R was uncountably infinite dimensional. So yeah, so we have so far established that every irreducible representation of the first Weyl algebra is infinite dimensional, probably, and the representation space is either KT or L2 of R. Yeah. So far, so good. Any question? No, so now we are going to see that whether there are any finite dimensional representations or not. Okay. So let's see. So suppose V is a finite dimensional representation. So that means V is a finite dimensional space on which the Weyl algebra acts. Then as we know, on Weyl algebra, we have yx minus xy equals to 1, right? Which was the definition of Weyl algebra. And if we take rho on both sides, we get this. We get this equation. And then if we take trace, so as we know, trace of AB is equal to trace of BA. So therefore, the left-hand side is 0, but the right-hand side is the dimension of V, because the right-hand side is the identity matrix. And the trace of the identity matrix is the dimension of the space. So we get that the dimension of V has to be 0. That means in characteristic 0, the finite dimensional representations have to be 0-dimensional, right? Unless some positive number, which is the dimension of V, is equal to 0. So you may think that I'm talking about, I'm being crazy here. How can a number, a positive number, can be equal to 0? Well, in certain fields, if we add 1 to itself multiple times, we may get to 0. And this number is called the characteristic of the field. And one can show that the characteristic of a field has to be either 0 or a prime number. So we have already solved the characteristic 0 case. Now we are going to look at the irreducible representations in characteristic P. Okay, I'm gonna take a quick water break now. And any questions? Okay, let's do it. So now we are in a field of characteristic P. That means if you add 1 with itself P times, you get 0. Okay, what is an example of such a field that if you add 1 with itself P many times, you'll get 0? What would be an example of such a field? Exactly. So ZP, well, that's 0, 1 through P minus 1. This is a finite field of characteristic P and size P as well. Right. So again, as before, previously we found that 0 is equal to the dimension of V, and a positive number is equal to 0 in characteristic P. That means P must divide the dimension. So in finite dimension, if Weyl algebra has a finite dimensional representation, then the dimension of the representation space is divisible by P. So suppose the dimension is non-zero, we can conclude that, well, the dimension is at least P, right? Because a number is divisible by P, so it has to be at least P or higher. Okay. Now, in order to find the irreducible representations, we look at the center of the Weyl algebra. So we have a result that the commutator of x to the I, y to the j with x looks like this, and the commutator with y looks like that. So if an element commutes with both x and y, that means that element is in the center, right? So, well, proving this is very easy. You just induct on I and j or whatever. So yeah, so as you can see, when is this term 0? Can someone tell me? When do we have that such a term is going to be 0? We don't have 0 anywhere. Yes. So yeah, I equals to 0, j equals to 0 is a way to make these quantities to be 0. And well, we have another way, is that if I is equal to P, because we are in a field of characteristic P, and P is 0 now. So that means if I and j are both divisible by P, then this term, x to the I, y to the j, this commutes with both x and y. That means this term is going to be in the center of the Weyl algebra, right? Again, why do we care about the center? Why are we finding the center? Any guesses? What's special about the center in the context of representation theory? We have seen such a result here, right? The elements of the center acts as scalars. So that's why we are gonna find what the center is, and we can then like work with that. So yeah, so from here you can see that x to the I, y to the j is going to be in the center if and only if both I and j are divisible by p. Right. So therefore, the polynomial ring generated by x to the p, y to the p, this is well, I made another typo. This should be a subset. So this is a subset of the center. In fact, you can show that the center is basically this. That means all the elements of the center is in this polynomial ring. All right. So basically, in particular, we have seen that x to the p and y to the p are in the center, right? So that means if we consider an irreducible representation, then the representation of these algebra elements are going to be scalars. Right. Sorry? Yeah. No, this is not commutator. The commutators are this. This is the like ring of polynomials generated by in x to the p and y to the p. Yeah. This is a very important like notational clarity, I guess. So yeah, let's move on. So now I'm going to throw another definition here. This definition also has a point, trust me. So suppose V is a representation of an algebra A. So a vector from the vector space V, we're going to call that vector cyclic if that generates V. What do we mean by that this vector generates V? That means if we act every algebra element on the vector space. I just realized I've just wrote the exact thing that's written here. So we have a vector V. We're going to call that vector cyclic. If we act every algebra element on that vector, we get the whole vector space. So if this happens, we call that vector cyclic. And what's the point? Is a representation is irreducible if and only if every non-zero vector is cyclic. So we have a characterization of irreducible representations. That is, a representation is going to be irreducible if and only if every element of the vector space, every non-zero vector of the vector space is cyclic. What's the proof? The one direction is pretty easy. That is, if a vector V is not cyclic, then this is a proper sub-representation. That means this is a proper subset of the V, of the representation space V. And if V has to be irreducible, we must have that the only sub-representations are 0 and V itself. So if V is not cyclic, then we get a contradiction. Conversely, if W is a sub-representation, then we get that, well, if we take an element from W, and since W is cyclic, we get that AW is equal to V. But then again, if W is a sub-representation, we must have that AW is a subspace of W. That means V and W has to be the same. So yeah, that's it. So that means we have proved that if a representation has to be irreducible, then every non-zero vector has to be cyclic, and vice versa. So is that clear to everyone? Any question? Okay. So let's move on. What is the point of proving this? So now we are going to look at the eigenvectors of the operator rho y to the power p. As we know, y to the power p, that commutes with everything, right? That means y to the power p is in the center. Since it's in the center, its representation is going to be a constant times identity, right? So let's say V is an eigenvector of rho of y. So then V is an eigenvector of rho of y to the power p as well, right? And since y to the power p is a scalar operator, so that means the eigenvalues of y to the power p is c. That means if lambda is an let me erase some of this. Yeah. So if V is an eigenvector of rho of y, then with an eigenvalue lambda, then lambda to the power p has to be equal to c. Right? Then V is a non-zero vector, and we are considering irreducible representations. So V has to be cyclic. All good? Because we have just proved that in a irreducible representation, every non-zero vector is cyclic, and here in this case we are taking the eigenvector of rho of y. Also, I have another question. How many eigenvalues does rho of y have? So we are working in an algebraically closed field. So that means the polynomial x, no, let's not write x. The polynomial t to the p minus c. This is a polynomial in the polynomial ring kt, and k is an algebraically closed field. Therefore, this polynomial has a root. So that means definitely lambda exists. But how many roots does it have? It's a degree p polynomial, so it has at most p distinct roots. But one can show that since k has characteristic p, it has exactly one root. Why? So we know that there's at least one root, right? Which is lambda. And my claim is that this is exactly equal to t minus lambda to the power p. So every freshman's dream is a plus b to the power p is equal to a to the p plus b to the p. Well, this is true in characteristic p. And we are in characteristic p, that's why this has to be equal to t to the power p minus lambda to the power p. And lambda to the power p is equal to c. So that means rho of y, this operator, has exactly one eigenvalue. This is useful later on. So again, let's go back. The eigenvector v, it's cyclic. Why? Because we are considering an irreducible representation, right? Okay. So therefore, the span of this is equal to v. Why? Because since v is cyclic, we know that like AV is equal to v, is the whole vector space v. And A is the span of what? A is the span of x to the I, y to the j, right? I, j being greater than or equal to 0. Why? Because we have stated that this is the basis for A. Well, by A, I actually mean A1. Yeah. So yeah, so since this is this spans A, and when we are writing A1V, we are basically saying that every element of A1 is actually acting on V. So therefore, this span, so this set, rho of x to the I, y to the j, V, this spans everything. All right. So now, since V is an eigenvector for rho of y, so that means if we act this rho of x to the I, rho of y to the j, V, we are basically gonna get lambda to the power j, rho of x to the I, V, right? Because lambda is the eigenvalue, is the corresponding eigenvalue for the eigenvector V. So yeah, so that means this spans the vector space V. Now, all the lambdas are, or lambda to the power something, these are scalars, so we can basically ignore them, right? So if we ignore them, we get that this thing, rho of x to the power I, V, this spans V. Again, since x to the power p is in the center, what do we get? Rho of x to the power p is basically some other constant C prime identity. Why is this important? Because in this set, rho of x to the I, V, where I ranges from 0 to all the non-negative integers, So here we're going to have some repetitions. Well, by repetitions, I mean that some vectors are not going to be linearly independent, right? Because v and let's say, I don't know, pth root of c prime v, these are not linearly independent, right? So therefore, we can restrict ourselves into the case I from 0 to p minus 1, because the x to the power p is basically some constant times the identity, right? Now, how many elements are there here in this set? Row of x to the I acting on v, where I ranges from 0 to p minus 1. So we have p elements here. So a set of size p spans everything in v, right? Therefore, what is the dimension of v? The dimension of, we cannot exactly say that the dimension is p yet, because we know that a set of size p spans. That means the dimension is at most p, right? And previously we have shown that the dimension is at least p, because p divides the dimension. Therefore, the dimension has to be equal to exactly p. So we have made some progress that in characteristic p, the finite dimensional irreducible representations has to be equal to the dimension equal to the characteristic of the field. Okay. So yeah, here I have written the thing I've stated earlier, that rho of y has exactly one eigenvalue. Why? Because pth roots are unique in characteristic p. And we have shown them, right? Okay. So now we are going to see that, well, it has one eigenvalue. Okay. But does it have multiple linearly independent eigenvectors? So that in the eigenbasis, we can write it into some diagonal matrix or some Jordan form or whatever. So let's say v1 and v2 are two eigenvectors for the eigenvalue lambda. And we can assume something like this, that v2 is equal to like rho of some polynomial in x v1. Why? Because the vector space v is a span of this, the span of rho of x to the I acting on v1, where I is from 0 to p minus 1. So if you take a linear combination of this, yeah, so since v2 is in this vector space, so that means v2 is going to be a linear combination of this. That means v2 is going to look like rho of some polynomial in x that has degree at most p minus 1, that being acting on v1. So that's v2. And our goal is to show that, well, our goal is to find out what exactly is the relationship between two eigenvectors. Okay, so now we're going to pull a cat out of our hat. What is this? This. The commutator of y and the polynomial in x is going to be p prime of x. Can someone tell me why this should be the case? Well, let's move back a bit where we found the center. So if you look at this, I'm going to just copy this thing over here. Oops. Yeah. So I have written that x to the I, y to the j. The commutator of this is equal to I, sorry, there was a minus sign. Minus I, x to the I minus 1, y to the j. So if we have a polynomial in x, that means there are only like the power of x and the linear combination of those, right? So the value of j is 0 in those cases. And if you like move y to the front, you'll capture another minus sign which cancels out with this. So you understand that this must hold, that the commutator of y and some polynomial in x has to be equal to p prime of x. Now, how is this relevant? So because, oops, sorry, because p prime of x is the commutator of y and p of x. So that's basically y p of x minus p of x y. And then like act rho on both sides, and you act that operator on the vector v1, we get this. And the left-hand side is what? The left-hand side is basically, no, we don't know the left-hand side yet. Sorry, my apologies. V2 was like rho of p of x acting on v1, right? So this is what? This is rho of y, v2. All right? Because that follows from this. And v2 is also an eigenvector. So that means this is lambda v2. And from this, we get that, well, v1 was also an eigenvector. So we get lambda rho p of x v1. Right, because v1 is also an eigenvector with eigenvalue lambda. And this is nothing but lambda v2. So this quantity is 0. Yeah. So since this quantity is 0, that means rho p prime of x has to be a 0 operator. So what does this mean? The derivative of a polynomial is 0. That means the original polynomial has to be equal to some constant. So therefore, v2 is a constant multiple of v1. So we have only one eigenvector and only one linearly independent eigenvector. So is this form like familiar to anyone? Does this sound familiar? That a matrix, well, we are in finite dimension, so we can always express our linear operator as a matrix. So a matrix has only one eigenvalue and only one linearly independent eigenvector. Can we express it into a diagonal matrix in some basis? Always? No, in order to write a diagonal matrix, we need to have like let's say we are working with an n by n matrix. So no, if we want to write the matrix as a diagonal matrix in some other basis, then we need to have n linearly independent eigenvectors. But we have only one linearly independent eigenvector. Yeah. So we cannot really write this in a diagonal form. Rather, we have the next best thing, which is we can write it as a Jordan block. That is, all the diagonal entries are the eigenvalue lambda, and all the sub-diagonal entries, which is the one above the diagonal, all the sub-diagonal entries are 1. Right? So yeah, so we have found what y looks like. So in some suitable basis, we can write rho of y as this matrix which has all the lambdas in one diagonal, and above that we have all ones. All right, is that clear? But we don't really know what this basis is. We only know that such a basis exists, but we don't know what it is. And if we don't know what that basis is, it's very difficult to like write what rho of x looks like in this basis, because we don't know what that is. Right? So yeah, we have computed what rho of y looks like. So we are going to have to compute rho of x, but we don't quite know what the basis is, which is why we're going to stick to our previous basis. That is the one I've shown earlier, that this. So this set consisting of rho of x to the power I acting on the vector v, where I is from 0 to p minus 1. What is v? V is an eigenvalue for rho of y. So yeah, it looks like this. That v, rho x v, rho x squared v, and so on up to x to the power p minus 1. So we're going to write the matrices rho x and rho y in this basis. Okay, so writing rho of x in this basis is very easy. Because why? Because what it does is it basically shifts. So if you act rho of x on this element, you just get rho of xi plus 1 acting on v. So we get the next basis element. except for the last case. Because if you act rho of x on rho x to the power p minus 1 v, you'll get basically rho of x to the power p v. This is not in our basis, right? Because x to the power p is in the center, so it acts like a scalar. Let's call that scalar mu. So this is basically mu v. So yeah, rho of x acting on rho x to the power iv is almost always rho x to the power I plus 1, which is the next basis element, except for the last case. Except for the last case, we get the multiple of the first basis element multiplied with the scalar mu. So how does this look like in a matrix format? So as I said, it shifts all the basis vectors to the one next, and the final one, and for the final one, it scales the first basis element by mu. So the matrix looks like this. It has some entries are 1, and that entry is mu. We all know what this means, right? It basically so if we act this matrix on the first basis element, it moves to the second one. So for ith basis element, so acting this matrix gives us the next basis element. Except for the last one, for the last basis element, if we act this matrix on the last basis element, we get the multiple of mu with the first basis element. So that's the matrix representation of rho of x in this ordered basis. So yeah, we have found rho of x in this basis. We have already found rho of y in another basis. So we are pretty much done, right? Well, almost, because we have to find what rho of y looks like in this basis. Before we move on, does this look familiar to anyone? Yes? Oh, this is a very important one. So he said that this looks like creation operators. Well, we know that, well, in quantum mechanics, we have two cases, bosonic and fermionic. For bosonic case, the commutator of the creation and annihilation operator is 1. And the other case, the anti-commutator is 1. So we are basically doing quantum mechanics, right? Because here as well, the commutator of y and x is 1. And we are finding a representation of that in finite dimension. So yeah, but I was expecting a slightly more concrete answer because we are in a math talk, right? We are not doing physics. Okay, I'm gonna come back to this, that whether this matrix looks familiar to anyone. Trust me, it is familiar to let's say more or less all of you. Okay, let's see how rho of y acts on these basis vectors. So if we act rho of y on the ith basis vector, which is this, so I have made use of another trick here, that is y x to the power I is basically the commutator of y and x to the I plus x to the I y. So using this trick, if we act rho on both sides, we get this equation, right? Yeah. And finally, another trick is that, so what is the commutator of y and x to the I? As we have seen before, the commutator of y and the polynomial of x is basically the derivative of the polynomial. So this commutator is basically I rho of x to the power I minus 1 time, so acting on the vector v. And as for this basically scales the thing, because what is rho of y? Sorry, what is v? V is an eigenvector of rho of y with eigenvalue lambda. So that means this thing is going to be lambda rho of x to the I acting on v, right? So, oops, sorry. Let me write this. So rho of y, if it acts on rho of x to the I v, it basically gives us first things first is lambda times the original input, rho of x to the I v. Then plus I times rho of x to the I minus 1 v. So it's basically lambda times the basis element I'm giving it as input right now, plus I times the previous basis element. So in the matrix form, it looks like this. All the diagonal entries are lambda, and all the this is called, I think, subdiagonal, right? All the entries in the above of the diagonal entries are 1, 2 through p minus 1. Okay, so we are basically done. So you all are hoping I'm gonna say we are done and you can go home. You just have to wait a bit, because trust me, there is a point I'm trying to make. So let's summarize. In characteristic P, the irreducible representation of A1, the Weyl algebra, looks like this in a matrix format. So rho of x is all the entries below the main diagonal is 1, and rho of y is lambda, plus all the entries above the main diagonal are 1, 2 through p minus 1. Do they look familiar? Anyone? Ring any so these two, do they ring any bell? Are there any three blue, one brown viewers here? Exactly. Yeah, I've made a reference to three blue, one brown because in one of his like linear algebra lectures, he basically shows what the derivative looks like in a matrix format. So yes, it's almost like a derivative, because, well, almost. Why almost? Because we compute the derivatives in an infinite dimensional case, right? That space is infinite dimensional. So yeah, you are right. This thing is the derivative operator, kinda. So we're going to consider the space on which the derivative operator acts on. We have taken this space, the space of polynomials. Well, we could have taken the space of, I don't know, differentiable functions or whatever, but in that case, we don't have an ordered basis. I mean, we obviously have a basis, but we cannot order it. Why do we need an ordered basis? To write a matrix, right? So the derivative in this ordered basis looks like this. Why? Because the first basis vector is basically 0. So all the entries in the first column is 0. If we add the derivative operator on t, we get 1, which is 1 times the first basis vector and everything else being 0, and so on, right? So we do get some hint of quantum mechanics here, right? Okay, so we know that like this looks almost like a derivative. What about the other one? What is the other one? Any guess? So let's go back to here. This one looks almost like a derivative. What about this? Should I spoil the answer? Okay, let's spoil the answer. So this is the matrix representation of multiplication by t on this polynomial space. So the first basis element is 1. If you multiply it by t, you get the second basis element, and so on. So yeah, or in other words, you can say that this is a right shift operator, right? So yeah, now let's look at rho of x. It has mu over here, right? So it looks almost like the multiplication by t operator on this polynomial space, except for t to the power p being identified with the scalar mu, which makes sense, right? So therefore, what is our representation space? It should not be kt, because firstly, it is infinite dimensional. I mean, kt is infinite dimensional, so it should not be kt. So it's a kt quotiented out by something, and we are making an identification here, which is t to the power p is equal to mu. So our representation space is going to be kt quotient t to the power p minus p. So yeah, on this space, the multiplication by t operators matrix representation is this. And for the other, so this one, this looks exactly like lambda plus the derivative on this representation space. So we are almost done here. So to summarize, the irreducible representations of the Weyl algebra in characteristic T on our representation space, this, the polynomials in T, where T to the power P is identified with the scalar mu. So on this representation space, X acts as multiplication by T, and Y acts as some constant times derivative. So yeah, now these are obviously familiar to physics people, right? Because we have stated in the beginning that all the irreducible representations for momentum and position and momentum operators are multiplication by x and derivative. So yeah, in characteristic p greater than 0 as well, that's the case. All the finite dimensional irreducible representations are either multiplication by t or some constant plus derivative. So what's next? Infinite dimensions and characteristic p greater than 0 as well, the representations of Weyl algebra looks exactly like that for k equals to the field of complex numbers. What do we do in quantum mechanics basically, right? So what's next? Can we define quantum mechanics for algebraically closed fields with characteristic p greater than 0? Well, there is no physical motivation for this because such a system is not physical. But that's not going to stop us mathematicians from diving deep into that. And the good news is some people are trying to do that. And that has some pretty exciting applications in quantum computations. But we're not going to go into that today, maybe for a talk in 2 or 3 months. So yeah. And if you are interested in quantum mechanics on finite fields or whatever, you can see the references. I have outlined the references here. So yeah, the references 2, 3, and 4, they deal with these things. And you don't have to take pictures of these slides because you can get the slides by scanning this QR code. So yeah, that's it for today. Now I'm open to questions.